I don't know about you, but I've spent a ton of time during quarantine watching a lot of amazing podcasts from people like Lex Fridman to Joe Rogan. And I've gained a ton of new perspectives over these last few months. But sadly, I'm not the biggest note taker per se, so a lot of those cool tidbits of information that I gained from watching those podcasts kind of just got drained out of my head. But today, I'm here to talk about a really cool application that I made that solves this problem by identifying when people are interested while they watch a video and extracting those segments to create a highlight reel of the moments that you're interested while watching the video. So what you just saw there is a demo of the application that I'm coining Mindframes. And it starts off by taking in a EEG stream through the Muse 2 headset, as well as a input video file, which is then projected onto the second screen where you're prompted to watch the video as you wear your headset. And once the video is finished, we take all of the brainwave data that we collected as you watch the video, as well as the input video, which is then sent to a server where we classify the interest points within your EEG data, use those time points to slice up the input video and extract the parts of the video that you were interested in. That edited video is then sent back to the front end where you're able to view and download the video, as well as understand at the specific time points when you were interested in the video, as well as how many times you're interested while watching the video. To start, we need to understand what EEG actually is. And it's not just some mystical brainwaves, but is actually the electrical signals that originate from your brain, and we can measure them from the scalp. And these signals actually tell us a ton about what's going on in the brain, from emotions to cognitive ability. In the case of my application specifically, we're looking for indicators within the EEG data that is highly correlated with interest. But it's not as easy as I say it is. There's a lot of processing that is required to really get what we need from this seemingly gibberish looking data. EEG data is known for being infamously littered with a lot of artifacts, whether it be from eye blinks or jaw clenches or power line noise. There's a lot of sources for noise within the EEG data. So it takes a lot of pre-processing to clean up the signal in the first place. I specifically used a 60 Hz notch filter to eliminate any environmental power line noise, as well as a 4 to 40 Hz bandpass filter to eliminate any type of heartbeat or eye blink noise below 4 Hz and muscular artifacts that are prominent above the 50 Hz range. Once the raw EEG signal has been cleaned and filtered out, I use a method of analysis called power spectral density to break down the overall EEG signal into its basic frequency bands. I then use the ratio between these bands as my initial features, as they've been shown to be highly correlated with interest. So for example, the ratio between theta and alpha has been shown to be highly correlated with visual and spatial attention. I calculate these band ratios for every single second within a 20-second interval for every single electrode in the Muse 2 and apply a simple moving average of 5 seconds over the 20-second interval. Finally, I take 4 different descriptive statistics from the average segment, which I use as input for my AI algorithm. Now, moving on to the AI algorithm that I use to classify interest, we gotta take a little step back to understand why it was justifiable for me to use a very simple machine learning algorithm. So I had to record all of my dataset from scratch because there were no open source datasets available online that used the Muse 2 as well as had EEG data that was related to the domain that I was looking for. So I really just had to watch a bunch of videos for a few hours and then label each 20-second segment with an interest marker. And this took forever. And out of that process, I was only able to get around 94 samples, and it definitely isn't much to train any type of large-scale model. So I ended up using a very simple Gaussian naive Bayes model for the sole reason that it has a ton of bias, which is helpful in reducing the chances of overfitting on the very small data set that I had. I also did implement data augmentation, so I was able to scale up those 94 samples to around 5,000 samples, but I was still reluctant to train any larger scale models just because of how little of the overall distribution those 94 samples actually account for. After all of the data augmentation and getting around 5,000 samples, I was able to train the naive Bayes model up to an accuracy of around 60%, which is predictable considering the fact that machine learning algorithms don't do the best job of classifying any EEG just because of how nonlinear the signal is. And especially with a simple model like naive Bayes, it's highly unlikely that I would have gotten any really significant results. So moving forward, it's definitely useful to use a more nonlinear model with higher variance, such as neural networks. Lastly, the predicted labels from the naive Bayes model would be sent over to a program that uses the MoviePy library to slice up the input video and output a stitched up video with all of the highlights from when the individual was interested while they were watching the video. In terms of the web frameworks that I used to develop MindFrames, I used Vanilla.js for the front end and a Flask server for the back end, as a lot of my scripts were written in Python, specifically my machine learning algorithm and my pre-processing. I also relied a ton on Brainwaves tools, as they provide amazing groundwork for developing with neurotechnology devices through browsers, and all of the WebSocket related stuff to connecting the Muse2 to the browser was done through Brainwaves. So that's it. That's how I built MindFrames. And this application was actually my first project that involved any type of web development. And I had a ton of fun mixing my passion for neuroscience with the internet. And you can find all my code in the description below, as well as a Medium article that dives deeper into the neuroscience behind my application, as well as a little bit of the code. Thanks for watching, and I'll see you guys later.